So this particular video is the culmination of a whole bunch of money and research, and not just mine. I have pulled all of this together. Essentially, if you add up like all of the totals that people have said that they've invested within this to get to all of these figures, it's about $5 million that we're looking at within research here. $5 million overall, like let's call it over 3,000 models trained in order to get these particular numbers and these metrics, etc. Kind of like, I think the best place to start is my like full opinions and thoughts overall with regards towards these things, right? So like, I mean, I personally have been in IT. I'm a dinosaur, so like since the early, like since the year 2000, I worked for Apple, and then like between 2000 and 2010, I worked for Apple, Intel, Dell, and HP. And there's actually a period there where I worked for HP, Intel, and CompUSA at the same time, and I got all three to agree that like there was no like competitive like interest within that, because it was like they were all like different suppliers on the same chain, right? But so no direct competition, and so that worked very nicely for me for a good period of time. I liked it, I enjoyed it, but within all of that, I was with these companies during some interesting periods, right? And then, like, very specifically, when I was working for Apple, there was a time and a thought back then that it would be possible to scale infinitely with regards towards like the Pentium processor, right? Like, at this time, it was the Pentium 4, and people were overclocking 3 gigahertz P4s at that time. I remember people had overclocked to, I think the highest I saw was like 5.5 gigahertz. And that's, I mean, that's doused in straight liquid, right? Like it's in a swimming pool basically to cool it down, which is the problem, right? That's the problem that people ended up running into was heat dissipation. So you could theoretically scale the Pentium 4 processor infinitely, like and have it go, right? But like the reason why like they never released anything above like 3.5, like there was one model I think that was like 3.8 gigahertz or so was like the highest commercial that they ever released, right? But they always stayed around 3.2 because above 3.2 gigahertz, that machine started to get very, very, very hot, and you deal with the laws of heat, the laws of thermodynamics, and the laws of physics that creep in that you can't do anything about. And we sidestepped that by introducing parallel processing, and then that was able to allow to scale for a while. But now the problem is that you're running into similar issues with scaling down, right? We can't scale down below 4 nanometers because you run into issues with gravity, flat out, right? Again, you run into the issues of physics, and the bottom line that we're learning, and that this culmination of this $5 million worth of research should tell you overall, is that digital spaces do not escape any of these physics laws that physical spaces do. Like I can't I'll save you $5 million right there, right? If you can comprehend that, you have saved yourself a bunch of understanding within this, that all of these systems, all of these processes, all of these laws, essentially how they're working and what they're pointing towards is that the laws of physics are present in these digital spaces, flat out, and they're all similarly tied to the similar laws of physics that you would within physical spaces. And how these models are working and learning essentially overall is via a method of compression and then storage within physical digital space, right? And then like to give you a simple kind of an example and analogy of that overall, let's say that you have a model, LLM model, and then you train it. It's freshly new, no concepts it has ever learned before, and then you teach it 2 concepts. You teach it cat and dog. First thing it's going to do is it's going to place the cat node in a particular part of its universe, right? We'll say it places it in the very center. and then you introduce it to dog, and then dog is in this instance orthogonal to cat, right? So then what will happen is that cat node that is in the center then needs to move. It moves and moves over here. So you have cat here and dog here. And then the more and more concepts that I introduce within that space, the more and more spread out the space can be, and the more memory that you need in order to enable to capture everything within that particular space, right? And then so within that, that's the physical laws that you're dealing with. And then no matter what type of data it is, whether it's words, etc., they're all paying a tax overall with regards towards these physical spaces. They need to be placed into a physical digital space, and the model needs to be able to associate and keep track of all of the relationships, and especially the distances within those relationships. Whether or not the model will be successful within that is determined based off of all the factors that go into that. How big the model is, how much compute it has, how much memory it has, how clean the data set is, how optimal your algorithm is. All of that goes into these different laws. And then but these different laws essentially make up laws of physics within digital spaces. And then so I can't stress that enough overall, right? But so within that, like, there's a bunch of laws that I have synthesized from this. So essentially what I've done just up front, I've taken a bunch of research papers. So like this one, for example, L squared M, Mutual Information Scaling Law for Long Context Language Modeling. This one here, Predictable Scale Part 1, Optimal Hyperparameter Scaling Law and Large Language Model Pre-training. These guys very specifically spent $1 million just on this to get their information here. And then so I take a bunch of these, like 6 of them, right? And then I combine and synthesize all of them, and then I synthesize it back on top of itself, and then I create notes off of this. I created like a whole bunch of different like podcasts, synthesize this data as much as I could to fully understand it, like fully process it out, and then here's the end result of like all of this synthesized together, like scaling laws as we know it at the moment as it applies to AI models. And then so this, you're not going to find like this whole synthesized research anywhere else, right? So here you go. First of all, starting off with hyperparameter scaling laws, the most interesting ones to pay attention to are the step law. And then the step law is within this research paper very specifically, and this is what they spend a bunch of money on, is to introduce this particular law, which essentially, which is this full-on equation here, right? And then so when it comes to LLM models and initializing the weights, what we do typically is we just do a random initialization of the weights, right? And it's been known for a long time that random initialization is bad. There's got to be a optimal way to do it, but no one knows the optimal way to do it. And then and it's expensive to figure out the optimal way to do it. So these guys did it flat out. And then so the optimal way to do it is based off of a batch size and your data set size. And then it's a combination and a algorithm that you can utilize based off of the batch size and the data set size to figure out what your optimal weights and your pre-starting weights should be. And then you just flat out compute this equation. And then within like 99.23% accuracy, this is going to be your most optimal weight settings that you could possibly set, as opposed to randomized weighting. And then so here you go, step law. And that's kind of the first scaling law that we have discovered that is definitive within these models. Also, what we've noticed is within this that these scaling laws are robust. They are the laws of physics, right? They hold true across spectrums of models, architectures, variation in model sparsity, distribution of training data, etc. These are like empirically validated like rules and laws, and step law is one of those empirically validated rules and laws within this. Next, we have the Mutual Information Scaling Law. The Mutual Information Scaling Law governs the long-range dependencies inherent in natural language. It diverges from the conventional notion of two-point mutual information scaling. As I stated at the top of this, right? Essentially what happens is like you take cat and dog, and then let's say we throw in a whole bunch of other animals, right? that distance grows and grows and grows and grows, and then also that complexity grows and grows and grows. So all of that needs to be taken into account, and that's where mutual information scaling comes in. And then, so first of all, you have long-range dependencies, and where natural language is replete with long-range dependencies, where the meaning and structure of a sentence are influenced by words that are far apart. And then, so again, cat has a strong relationship to dog, but they would be orthogonal, right? And then model state size. So to effectively model long context links, the size of a model's state for storing past information needs to scale at a rate faster than the bipartite mutual information scaling. This is known as the long context language modeling condition. So essentially, you can know upfront and calculate via your model size and the dataset size whether or not your model is actually going to succeed, or it has enough brain power to be able to compute all of the distances that you want it to compute, utilizing the long context language modeling condition, or the L2M condition that they introduced within this research paper. The L2M condition very specifically stipulates a mathematical criterion for models to be machine learning capable. It states that the history state of a model just before a given token must satisfy a specific scaling relationship. So it all comes down to tokens there. Furthermore, we can break down neural scaling laws. Neural scaling laws pertain to the power law relationship that exists between a model's performance, its architectural attributes, and the computational resources required for its training and inference. First of all, we have power law relationships. These laws posit that the performance of a model scales as a power law with respect to factors such as the number of parameters, the size of the training data, and the computational budget. All of these scale not in a linear fashion. It scales logarithmically. So the more higher that you're trying to go, the more expensive it becomes, flat out. So within this, we can look at a bunch of frameworks and prove that out. The secondary aspect that I want to dive deep within this is to apply this to each individual model architecture, because within all of this, there's a very unique pattern that comes out of this, which is, so the best way to look at this overall is that when it comes to computation and trying to solve any sort of problem computationally, you have to pay a compute tax to solve that problem. How expensive the tax is depends on how big the problem is, how much data is required to solve it, how big the model has to be to solve it, etc. But all of these taxes need to be paid. So if you calculate all of the taxes up front, you can calculate how much taxes that you need to pay in order to actually successfully compute something. And then within that, you can decide how you want to pay taxes. And then different models pay the tax differently. Like Transformers, very specifically, pays this tax differently and in a very different way than, say, RNN models or other solid state models, which is very significant, right? So then, why exactly does Transformers operate differently than RNNs? That's been kind of a challenge to figure out. It's because Transformers pay the compute tax differently. The Transformer model pays the compute tax up front. It's like a prepaid model. So, and Transformers very specifically pays this compute tax via the attention mechanism. And that's very important, right? So the model is prepaying the tax. So every token sees all other tokens at every layer. This requires quadratic computation during training, which is the problem with this prepayment method, right? But at inference, once trained, they retrieve information efficiently with the pre-computed key value caches. The bottom line here is that attention scales quadratically, right? Attention is subject to this. So this is the tax, the quadratic attention tax that Transformers models pay, meaning that the bigger the attention size that you want, the more tokens that you want the attention to pay to, you pay the tax, every doubling of that instance, you're paying 4 times as expensive. And then so it gets more and more and more and more expensive, and then there's nothing that you can do. You can't get around paying the attention tax within this instance, right? The quadratic scaling of the attention mechanism is where and how the transformers model is paying the tax. And then so again, it's paying it upfront, and it's paying it in a unique way as opposed to like RNN models, right? So transformers are a prepaid model, whereas RNNs, how they're paying the tax, they're pay as you go. And then you can see this when you play models, right? So RNNs and all of their variants like LSTMs, Mamba, GRUs, etc., they process input sequentially, one step at a time. So instead of computing all of the dependencies up front, they pay the tax gradually, and then they pay it during inference. And then so this is good, right? Because they pay as you go. But where it struggles is with those long-range dependencies, and then when you get into parallelization, which we know, and then inference time. If you run out of money, you're done. The model is toasted, right? And then the model will keep going until it runs out of money because it's just paying as you go, right? And then so it's just going to keep paying and paying and paying, and then eventually your wallet will run out, and then that's where the falls off. So essentially, to compare these two models and these two architectures, you have quadratic scaling as opposed to linear scaling. So its RNNs are cheaper as you go, but more expensive. They will struggle, and you'll run out of money essentially if you try to scale them up big over time, right? And then we can take this and look at this a step further. So I focus a lot on this channel on alternative architectures to transformers. So how would all of this and how does all of this function within that, right? And I can explain that out to you as well. So so we've looked at transformers and like RNN type of architecture. So prepay and pay as you go. What about like different architectures like HDC or hyperdimensional computing? Hyperdimensional computing is unique, right? It's a pay once and retrieve instantly. So whatever, like you say this is the problem, and it'll say, okay, it's $5 to solve this problem, or if it's a more complex problem, it's $20 to solve this problem, and then you pay the tax, and then you that's it, and then then you have your model for whatever you pay the tax for, right? You own the model for that particular solution. Bottom is kind of like how it works out, right? And then so your training cost is very low. Basically, like it's cheap upfront to do this, but essentially the retrieval is cheap, but you're not actually paying the compute tax and the encoding, right? So it's not learning in that sense. So since HDC doesn't use gradient-based learning, the tax paid is paid in how well the encoding captures essential relationships between data points. Analogy of this is HDC is like a one-time toll road payment. You encode everything up front, and then retrieval's nearly free. You pay the toll and you can ride it unlimited times, right? Swarm algorithms are like almost the orthogonal opposite of this. So swarm intelligence mimics decentralized decision-making in nature, like ant colonies, particle swarms, etc., and it spreads computation across multiple agents that explore solutions dynamically. So every single agent is paying a small toll. They're paying the small tax, right? Every single one. And then so what that means is that the more agents that you have within the system, the more taxes that you have to pay. You're paying think of it like a standing army tax in this instance, right? The bigger that your standing army is, the more taxes that you have to pay. And then you also have to pay, and then you can also train your army for like different battles and through different battles, right? And then so you're paying the standing army fee, and then also the battle fee, like the battle tax for each time that they go to battle. So if you have 50 agents and then they go to battle 5 times, you're 50 times 5, right? And then that's kind of how you would pay the compute tax in that instance. So swarm methods are like paying a collective community tax. Each agent pays a small portion, and the total tax is shared and spread across the total units. And then also too, they take full advantage of parallel searching, which means that your taxation is always linear as opposed to quadratic. So when you scale this up and up and up, it becomes cheaper, far and far less expensive than transformers to ever scale up, because you don't have that quadratic scaling problem, but you do have to pay the tax still among the individual agents. Next, you have genetic algorithms, which are different overall than both of these architectures, right? So, and the tax is different. The tax for a genetic algorithm is like an iterative tax with mutation fees. You're paying like like with genetic algorithms, you pay like a sliding tax, and then every single time that you're evolving and you're mutating, you're paying a toll, right? Like so, it's like those mutations are your tolls, and then it doesn't really matter in that instance how many agents are mutating. Like it's the fact of mutation is what this whole is based off of. So genetic algorithms evolve solutions through selection, crossover, and mutation, meaning that they iteratively refine populations rather than learning through direct parameter updates. In this instance, the problem is that evolution is expensive, right? So each generation of solutions is tested and refined, meaning that compute grows with the number of iterations. And then it's like the number of tests that you're doing scales your compute far more dramatically under this model than any other model. So if you run it for like 20 iterations, you're going to toast you're going to run out of money, basically. But within that too, convergence can be slow, right? Like these models want to run for a lot of iterations because they're evolving, right? They want to evolve as much as possible, but it gets more and more and more expensive the way that you do that. So you have to try to frame the algorithm in enough to give it enough evolutionary freedom and make it cost effective is kind of the bottom line, right? And then so kind of an analogy overall is that genetic algorithms are like paying for multiple rounds of expensive prototype testing. Each iteration costs more compute until the best design is found. And so it's just going to iterate and iterate, and you will, under this solution, like this is like the Bill Gates solution, right? Like it's like if you have Bill Gates money to devote to compute, then you'll find the solution, right? You just throw money at it, and eventually it will, and then or you'll run out of money and go bust. So go big or go home with that. And then so essentially the bottom line overall, summing this up, is that like transformers are again like a prepaid tax with like recurring fees up front. And then I give you this full table, right? So you can compare transformers to HDC, to swarm, to genetic. And then so it's essentially we've got like our different tax types and our different ways of paying the taxes, and then the different areas that the different taxes come into play. And then as you can see, like this all plays into standard physics laws across anything else, right? I can't stress that enough. So like, for example, with transformers, you're offsetting and prepaying that tax essentially, but by doing that, you run into quadratic scaling, right? You can't like just prepay forever. There's a penalty for too much prepayment essentially. Right? And then whereas like HDC, you know what your upfront costs are going to be, but then you always you're always stuck with that solution, right? If you want to test another solution, it's another $5, and then another $5, and another $5, and then so that adds up that way over time. Whereas genetic algorithms, you don't know how much it's going to be upfront, and unlimited compute and unlimited money, it will solve the problem. But is it going to solve it within the amount of finite money and compute that you have? And then that's what the question comes down to, right? So the final takeaway is that all systems pay. Some of them pay smarter than others. So they will all pay the tax. They all pay the tax differently. And there's trade-offs to paying the tax differently. And then that's what it all comes down to. And then knowing these things up front, you're operating under the same laws of physics as everyone else, right? The laws of physics are the laws of physics, and that's the way that it goes. And then so I'll leave all of that here with this particular video, and this is the scaling laws of AI model computation. I'll leave a full link to this document that I went over here, which is like kind of like this is the culmination of everything that I've put together on this for you. So if you like this type of content, please like and subscribe. Thank you very much.